Bismillahirrahmanirrahim. In this video, we're gonna focus on heat engines, efficiency, the Carnot engine, and refrigerators. Actually, you can see in the module chapter thermodynamics, page 43. Okay, so let's begin. Okay, last meeting, we know that the first law of thermodynamics is basically a statement of the conservation of energy. The change in internal energy is equal to Q minus W, work. Q as heat and W as work. Okay, and so let's say if this box represents the system, all right, and if we add 400 joules, that's Q, heat that is absorbed by the system, and the system performs 200 joules of work, so it expands 200 joules of energy. In here, the system gained 400 joule and lost 200 joules. So the internal energy that is gained by the system is 200 joule, which is positive. Okay, this is the delta O, the inner energy. Okay, and this is the conservation of energy, the main idea behind first law of thermodynamics. Okay, now let's move to heat engines. Okay, this is our topic for today, heat engines, mesin pemanas. What exactly is a heat engine? Actually, you can see in the module, page 43. A heat engine is basically a device that converts heat energy into mechanical energy or work. So, jadi mesin pemanas ini adalah suatu alat untuk mengubah energi panas menjadi energi mekanik, gitu ya, atau kerja, work. Okay, so let's say we have a hot temperature reservoir. So let's say we have this is as a hot reservoir, also with temperature 500 Kelvin, for example. And if we have a low temperature reservoir, okay, this is low, or cold, the cold one, which is at, for example, 300 Kelvin. And let's say it's a box in here. It's a box is in here. In the middle is the system. Okay, the system or the object, the object that we observe. We call it system. Okay, heat will naturally flow from hot to cold, right? Okay. Okay, cold. Let's write this as cold. Okay, naturally the heat will flow from hot to cold, right? Okay, and so the amount of heat energy that flows into system or that is absorbed by the system is known as QH. The heat that is absorbed by the system, we call it as QH, and the amount of heat energy that is expelled by the systems into environment or into the cold temperature reservoir is, we write it as QC, cold heat gitu ya, QC. Well, as heat flows from hot to cold, the systems can absorb some of that heat energy and use it to convert into mechanical work. So there will be work in here. Okay, that's a heat engine. So the heat engine is not able to take all of the heat of energy that it absorbs and convert it to the work. It takes a fraction of that energy. Most of the energy is expelled into the environment, but the heat engine takes some of it and convert to mechanical work. Okay, from here we can see that the work is equal to the difference between QH and QC. QH minus QC, right? Okay, and we have efficiency of heat engine. The efficiency of heat engine is equal to work over here divided by a QH. This is the efficiency times 100%, of course. Okay, you can see the example of heat engine, page 45, number 8. In this question, we have a heat engine absorb heat. Okay, absorb 1000 joule heat. Okay, so we have Q 1000 joule with symbol positive because it is absorbed from hot reservoir. So we can draw it. Let's say this is the system, and the system is absorbed Q as 1000 joule and wasted 800 joule heat to the cold reservoir. This is the work. Oh, no. I'm sorry. This is the wasting energy. So this is the from hot reservoir, and this is the wasting, yang terbuang gitu ya, yang terbuang. We write it as QC, 800 joule. How much the efficiency of the engine? Okay, the efficiency of heat engine is work divided by QH times 100%. So efficiency is work divided QH times 100%. Work. Okay, if the system absorb 1000 joule and waste 800 joule, so the system work use the heat or converts the heat to mechanical work, to mechanical energy. How much? Okay. Masuk 1000, keluar 800. So this is 200 joule, right? Okay. So in here we have formula that work equals to QH minus QC, right? Okay. Kind of 1000 minus 800, so it will be 200 joule. So the final work is 200 divided by 1000 times 100%, it will be set okay, 20%. Okay, so this device is 20% efficient or 20% of the heat energy that travels through the system is converted to mechanical energy. So it's only 20%. Jadi hanya 20% yang panasnya bisa dipakai kerjaan. For example, piston, for example, kendaraan gitu ya. Atau pemanas ruangan. Jadi yang kamu pakai itu yang kepakainya hanya 20%. Where the others, 80%. The other 80% is expelled or escapes to the environment. Gitu ya. 80%-nya hilang ke lingkungan, gitu ya, keluar. Okay, that's heat engine. Where the symbol or the information of W is work with unit joule and QH which is the amount of heat absorbed from the hot reservoir with symbol also in joule because that is heat. And QC in here is the amount of heat released or wasted to cold reservoir. Joule as well. Alright, I forgot to tell that in here 500 Kelvin we can write it as a hot temperature TH, and this is 300 Kelvin we can write as cold temperature TC. Okay, so another formula of the efficiency also we can write as 1 minus the cold temperature divided hot temperature times 100%. Okay, that's it. Let's talk about the Carnot cycle, Carnot engine. Also, you can see this material in module page 43. Carnot engine is basically the ideal model of a heat engine. Ideal model, yeah. It was designed to represent or to obtain the maximum possible efficiency, so it's simply an ideal model. So no other engine can have an efficiency that's greater than the Carnot engine. So the Carnot engine is the much greater than other machine or other engine, at least as far as we know. Okay, first let's draw the PV diagram for this. PV diagram, pressure and volume. This is P and this is V, PV diagram. And for Carnot engine has two cycles. In Carnot engine has two cycles that consist of two adiabatics processes and also two isothermic adiabatic or isothermal processes. Sorry. Right. So in Carnot engine there are two cycles. Okay, let's draw it. Okay, start at position A in here. The first step of the Carnot cycle, we have an isothermal expansion A to B. This is expansion. So going from A to B, during this isothermal expansion, heat is added. Okay, heat is added to system, and the machine or the engine will perform work, which is positive. Anytime a gas expands, the work done by the gas is positive. Okay, and in second step, going from B to C, okay, B to C, we have an adiabatic expansion, and during an adiabatic process, no heat transfer. Remember, in adiabatic process, there is no heat transfer, so Q will be right as 0, and the engine performs positive work during this process, okay? Because a gas expands. Okay, now going from C to D, okay, C to D, all right. This process known as an isothermal compression. The volume is compressed. Isothermal compression. Remember, for any isothermal event, delta T is 0. Isothermal process, constant temperature, yeah. So delta T, or the change in temperature, is 0. But going from C to D, heat is released. Okay, from here, heat is released. This is hot reservoir, and this is cold reservoir. Okay, from the heat will transfer or release from the engine to environment. And because the gas is being compressed, well, the engine performs negative work. Okay, this is negative work because the engine is compressed. Okay, to complete the cycle from D to A is adiabatic compression. Okay, this is adiabatic compression. Okay, which performs work that is negative. Okay, that's it. Okay, actually there's kind of similar of graphic between adiabatic and isothermal, but what is in English? In bahasa isothermal lebih landai, atau adiabatik tuh lebih curam, gitu ya. Adiabatik lebih curam. Tapi sama-sama melengkung. Okay, A to B is isothermal expansion. B to C is adiabatic expansion. C to D is isothermal compression. And D to A is adiabatic compression. Okay. So this is Carnot engine, the cycle of Carnot engine. Okay, how about the efficiency of Carnot engine? The efficiency of Carnot engine is 1 minus the cold temperature divided hot temperature times 100%. Okay, right? Yes, that's it. And you can see the example of Carnot engine, page 45, number 9. Okay, number 9, the efficiency of Carnot engine is 60% if the cold reservoir, cold reservoir, C itu cold ya, C cold, kalau H itu hot gitu. Okay, TC is 27 degrees Celsius, and let's convert to Kelvin, it will be like 300 Kelvin. And what is the temperature of the other reservoir? So if in here cold, so the question is hot, the hot one. How much temperature in hot reservoir? Okay, let's use Carnot engine efficiency. The efficiency of Carnot engine is 1 minus cold temperature divided hot temperature times 100%. Yeah, remember this formula. Just put the number. This is 60%. 1 minus 300 divided TH times 100%, which is, we can divide it percent in here. So 10 will be moved to here. So it will be 6 divided 9. And 1 minus 300 divided temperature of hot temperature. And okay, you can move 300 divided hot temperature equals to 1 minus 6 divided 10. The result will be 4 divided 10. Okay, so the H is 3000 divided 4. It will be 750 Kelvin. That's the answer. Okay, it's air conditioner. Air conditioner. Okay, these devices work in the opposite direction compared to a heat engine. In a typical heat engine, heat flows from hot reservoir and move to cold reservoir, right? Okay, like this. And this is the system. For example, this is the big box as system. Okay, the heat flows from hot to cold like that. And yeah, so heat flows from hot to cold and convert some of the heat become work or become mechanical work. But in refrigerator, let's erase this. Okay, in a refrigerator, electricity is used to perform work. Okay, so we need work. We need work from electricity to pump heat from cold to hot reservoir. Okay, well, the work is still the same. The work is still the same. That is hot heat minus, this is W, yeah, work minus QC. Okay, that's still the same. So this is QH, yeah, this is QC with high temperature, and this is with cold temperature. Okay, so QH in here is equal to work plus QC. Okay, you can see from the draws from the graphic, yeah. Okay, in refrigerator we have the coefficient of performance. The coefficient of performance, the coefficient of performance the coefficient of performance, or in symbol K, that is K actually is equals to QC divided W, or K also can write as the low temperature, the cold one, divided as hot temperature minus the cold one, without 100%, yeah. Okay, in coefficient of performance, we don't have to write, we don't need percentage in here. Okay, for example, number 10, if The temperature of a color coil in a freezer is, the cold one is minus 15 degrees Celsius, convert to Kelvin, that is 258, right? And the low temperature at the high one, the hot one is 30 degrees Celsius, change to Kelvin, convert to Kelvin, it will be 303 Kelvin. And the question is the working coefficient. Okay, the working coefficient is equals to the cold temperature divided by the hot one minus the cold one. And put the number in here, 258 divided 303 minus 258. So it will be 5.7. That's the result. Okay, so the maximum working coefficient for this freezer is 5.7. Okay, I think that's all for today. This is the material for today. And please, if you have watched this video, please let me know by doing these exercises, number 9 and number 10, and please upload your answer to Schoology by today.